Welcome back to Blemmings Labs. Our next speaker has a pre-recorded talk, and so he's actually live with you in the chat in the Blemmings Lab channel on Venulus. And this talk is large virtual address support, 52-bit in ARM64 kernel. So Bhupesh Sharma is the presenter, and Bhupesh works with Red Hat as part of the Red Hat kernel team. He's been hacking on bootloaders and kernels for the past 14 years. He contributes to Linux, EFI, U-boot, bootloader, codebase, and also to user space utilities like Kexec, I can't actually pronounce that, sorry, KEXEC tools, and Crash Utility. He also co-maintains Crash Utility tool upstream, and bringing up a silicon after hardware tape-out is his passion, and he's interested in pre-silicon emulator and simulated design methodologies as well. So what we'll be doing is he will be taking and participating in the conversation with you all on the chat, and then he'll be joining me here in StreamYard to be taking some questions live after the presentation. The pre-record goes for about 24 minutes, and so I'll see you here in the live Q&A afterwards. Bhupesh, thank you all.
Hello everyone. So I welcome you to this session on large virtual address space support 52-bit in ARM64 kernel. We're going to talk about the relevant implementation details and discuss some pain points. Hi, I'm Bhupesh Sharma. I work with Red Hat, and I hope you are taking good care of yourself during these trying times. Usually, large address space support is a very frequently talked about topic, but can become boring quite quickly. So in this talk, I'll try to demystify a few details. So let's open up the mystery box a little. Okay, so here we go. Okay, a bit about myself first. I work with Red Hat as part of the kernel team. This is my snap from the last in-person conference I attended in 2019. So missing those days when you could travel freely, right? So bootloaders and Linux kernel interest me. I mainly contribute to several upstream open source projects like Linux, EFI, and U-boot bootloaders. Recently, I have also started contributing to user space utilities. So for example, Kexec tools and make them file. I also co-maintain the upstream Crash utility tool in the user space. Right, so let's see what we are going to talk about today. First, we will talk about the large virtual address support for ARM64, the what and the how. Then we are going to discuss a bit about the existing kernel memory layout on ARM64. Thereafter, we will discuss about flipping the ARM64 kernel memory map for accommodating the increased memory range. Then we will talk about something very important, user space. So what happens to the existing user space applications which expect pointers from the 48-bit addressing space from the kernel? Also, we will discuss about some of the user space applications. They might be broken after these kernel map changes. So we'll talk a bit about them. Thereafter, we will discuss about how a user space application can explicitly request addresses from the 52-bit range. At the very end, I'll try to share some suggestions and next steps. Right, so let's begin. So I hope all of you have heard about the 64-bit hardware. Mainly, how the 64-bit hardware is getting more and more popular, and it's really moved from the good to have range to at the minimum required feature, for various computing use cases. Very quickly, it has moved from this domain to that domain. So from edge routers to servers, all the way up to supercomputers, you can think of several existing use cases like that for 64-bit hardware. And the 64-bit hardware allows you to, well, in theory, connect to about 16 exabytes of memory. So we recently saw a server with 64-bit terabyte memory connected to it. Huge, right? So we are seeing more and more such use cases which require addressing address ranges larger than what is normally allowed by a 48-bit virtual addressing CPU. However, do note that there are some limitations. That is, not all processors support the full 64-bit virtual or physical addressing space. We'll talk about them in the upcoming slides. Also, do note that I will focus this talk mainly on the ARM64 architecture and mainly talk only about the virtual address space requirements. So I'll not deep dive into the physical address space requirements, but you'll get an idea about that also by looking at the slides. So just to save the time, I'll mainly be talking about ARM64 and the virtual address space requirements. Right. So in the previous slide, we talked about the architectural limitation in the CPU design for addressing the complete 64-bit memory map. Let's see how two well-used architectures, champion in their own right, fare in terms of the virtual addressing capabilities. So these are the Intel x86, the 64-bit, which introduced the 5-level page table support in its 10th generation Intel Ice Lake cores. So cores like Core i3, i5, and i7, these support 5-level page tables, which allow them to address up to a 57-bit virtual address space. Note that this bumps the possible virtual addressing space all the way up to 128 petabyte, and the physical addressing space is bumped to 4 petabyte. Quite a leap, right? Quite a big leap. On the similar lines, ARM64 recently introduced two new architecture extensions, in fact, which are called the 52-bit addressing extensions. So these are the ARM v8.2 LVA and the ARM v8.2 LPA. So ARM v8.2 basically specifies the ARM v8 application profile architecture 8.2 version, which has two extensions, the large virtual addressing and large physical addressing extension. So it is expected that ARM64 cores with these extensions will allow virtual and physical addressing space all the way up to 4 petabyte. Again, quite a big jump from the earlier maximum support of 256 terabytes achievable with the 48-bit hardware support. Okay, so just a quick recap of the previous slide from ARM64 perspective. The ARM v8.2 application processors from the Cortex-A family, which is the application profile family, such as the A55, A75, and A76, provide two extensions, the LVA and the LPA extensions respectively. So the CPUs with these extensions will provide a 52-bit addressing capability, which is quite a big jump from the earlier support available with 48-bit address space. This makes these ARM cores, these ARM64 cores, possible candidate for very high-end server-like use cases, which also require a low power profile, which is actually a USP of ARM cores. Okay, so we talked about address spaces and all in the previous slide, but what really happens in the background? So when a CPU tries to read from or write to an address, so what happens that? So I'm sure folks here know a lot about MMU hardware already, and I don't really want to go into the deep dive of MMU and what it does, in terms of separating the virtual and physical address spaces. But still, let's see a simple example, and to understand how a virtual address, when the CPU issues a virtual address, how the MMU works, and it tries to find out an equivalent physical address for the same. So here I'm taking the example which is specifically suited for ARM64 architecture, but the basic underlying principle is valid for other architectures as well. So when an ARM64 processor issues a virtual address for an instruction fetch or a data access, the MMU hardware basically translates the virtual address to a corresponding physical address. So this happens via what we call as a translation table walk. So usually a translation table walk comprises of one or more translation table lookups. So in this example, I have shown three translation table levels. Level 1 is the topmost table level, and level 3 is the lowermost. So each translation table lookup basically returns you a descriptor, which tells you either of these two things. So first, it can actually tell us that the entry is the final entry of the walk. So in this case, the entry contains the final physical address and the associated permissions and attributes that are required for these access. Or it can indicate that there would be an additional level of lookup which is required, And in this case, the entry basically contains the translation table base address for the next lookup. Now, in the next slide, let's look at how software, particularly the Linux kernel, supports these translation tables. Okay, so in this slide, we will try to see things mainly from a Linux point of view. So in the ARM64 architecture, we currently have support for page sizes of 4K, 16K, and 64K. Of these, normally page sizes 4K and 64K are used. So 4K is mainly used for embedded profiles and 64K is mainly used for server profiles. So let's look at the virtual addressing ranges supported when the 4K page size is used. So first is the 39-bit addressing range, which allows 3 translation table levels. The second is the 48-bit addressing range, which allows 4 translation table levels. So you can refer to the ARM64 memory documentation page inside the Linux kernel documentation for more details. Right. So furthermore, continuing on the Linux details, for the 64K page size, which is normally used for the server profile, let's look at the virtual addressing ranges that are supported. So first is the 42-bit addressing range, which allows 2 translation table levels. The second is the 52-bit addressing range, which allows up to 3 translation table levels. Note that the translation table levels for 64K page size and 48-bit addressing versus the 4K page size and 48-bit addressing are intentionally kept the same. This is required to minimize the effort required for moving from 48 bits to the 52-bit address space. So just the number of descriptors in the first translation level are expanded for the 52-bit addressing. Again, you can refer to the ARM64 memory documentation page inside the Linux kernel documentation for more details. Okay, so in my view, the best way to understand the 52-bit address space on ARM64 and how actual translation happens is to have a look at an example. So we saw in the previous slide, that 52-bit support is only available with a page size of 64K on ARM64, and it requires 3 levels of page tables. So let's see how the 3-level kernel page tables, that is the PGD, the PMD, and the PTE, fit into the picture here. So let's start from our earlier premise. The core issues you a 64-bit virtual address, and we want to find an equivalent physical address for the same on ARM64. So on the extreme left of the picture, you can see the TTBR select bit, so which is bit number 63. It selects basically between the kernel space and the user space addresses. So if I can call it the TTBRX, so the TTBRX would basically hold the base address of the level 1 page table. Now, bits 51 down to 42 in the incoming virtual address will tell us about the PGD index in the level 1 table. Similarly, bits 41 down to 29 in the incoming virtual address will tell us about the PMD index in the L2 table. And lastly, bits 28 down to 16 in the incoming virtual addresses will tell us about the PTE index in the level 3 table. So finally, the derived PTE value and the lowermost 16-bit of the incoming virtual address, these would be combined to determine the final physical address value. So I hope this example makes things a bit more clearer. Again, feel free to refer to the ARMv8 address translation documentation from ARM for more details. I have added the link for that in the slide. Right. So we come to an interesting aspect now. How do we decide the kernel design approach? To support both the older ARM64 CPUs, which don't support the 52-bit extensions, and also support the new ones, which do. So in the kernel, we have basically decided to keep an approach or to select an approach which keeps a single binary and makes the decision at an early boot time to check if the underlying hardware supports the 52-bit extensions. If it does, the kernel uses the 52-bit virtual addressing mode. Otherwise, it fallbacks to the default 48-bit or lower virtual addressing mode. So let's take an example of two platforms, the Ampere eMag ARM64 workstation, which doesn't support the new extensions, and the newer Fujitsu FX 700, which basically, it claims support for the ARM v8.2 extensions. So, as the figure demonstrates, the decision about which addressing range to support is made at a early boot time, and accordingly, either the 48-bit or the 52-bit addressing range is used. Again, you can refer to the ARM64 memory documentation page in the Linux kernel documentation for further details on how to understand, this kind of a decision is made at the early boot stage. Now, fair enough. So, on this slide, we will just look at, quickly at the kernel variables, which the kernel code uses to make sure that it handles both the 48-bit as well as the 52-bit virtual address as well. And also is able to make an early boot time decision to switch to either the 52-bit virtual address space if required, or stay back at the 48-bit virtual address space, which is a default case. So it uses mainly three variables, right? So there are other variables as well in theory, but not very useful for this discussion. So let's discuss about these three variables only here. So one is the v underscore bits, which basically denotes you the maximum size of the virtual address space. The next one is va bits min, which is basically it denotes the minimum size of the virtual address space. And then the most important one, which is the va bits actual. It basically denotes the actual size of the VA space. So if you want to really check the VA address space range supported by your running ARM64 kernel, you should look at the value reported by this variable. So you can look at the value through a debugger or any other way, but it will actually tell you what is the virtual address range that is supported by your running ARM64 kernel at the moment. So let's move a bit further. Okay, so do we need to keep something additional in mind when we talk about increased memory map support on ARM64? Well, surely we do need to keep in mind that the kernel memory layout actually was flipped starting from kernel version 5.4, and this was done to allow a larger VA space support. So let's look at the figures on the slide to understand this better. So by default, with up to 48-bit virtual address support, the ARM64 kernel memory map looks like something shown on the left side. The direct linear map was placed at the farthest end of the memory range, whereas the kernel text range was kept near the lower address ranges. Now for the 52-bit support, we flipped the kernel memory map but decided to keep the kernel text addresses same as earlier. So this was to ease the transition from the 48-bit to the 52-bit address space. So the direct linear map range goes, it goes to FFFF followed by all 0 addresses, whereas the after a gap, the kernel address sanitizer, kernel text, and other addressing ranges are kept. So this flipped kernel map causes some interesting problems in the user space, and let's look at them in the next slide in more detail. Right then, so what happens in the user space then? Unfortunately, due to the flip in the kernel memory map, a few user space applications, especially the ones which are used to debug live kernel or which are used to analyze the VM code dump from a crashing kernel, they get broken. So the main reason behind the same is that these applications also need to perform a virtual address to physical address conversion and to find out an offending crash location. So for example, they also need to do a translation table walk to find out the offending crash location. So similar to the kernel space, these utilities should also modify their translation table walk code if they are being run on kernel version greater than 5.4. So I have proposed some fixes already for these utilities in the upstream channels, upstream mailing lists. So while a few have been accepted already, the others are still under discussion. So you can see more details on these fixes by clicking on the links that I have shared in these slides. But the idea is that if you are using a debugging application on these ARM64 kernels, which are greater than or equal to version 5.4, you might have some issues. So I know the $1 million question right now popping up in your head would be that other than the debugging applications, what happens to the other applications? Are they broken? Which are probably not used for debugging kernel per se. So these existing applications actually expect a maximum address from the kernel, which is actually 48-bit. So basically, do they break, or now because the kernel started returning addresses in the 52-bit range? So the answer is no. Basically, we decided to keep a opt-in model for the user space applications. So the kernel will be by default returning an address from the 48-bit range. So the existing applications will keep working well. However, newer applications can actually pass a hint parameter to the mmap call, for example, to explicitly request a address in the 52-bit range. Right then, so what are some of the pain points and the next steps? The first step is actually to fix the broken debugging related user space applications, which is a work in progress, and I hope that these all will be fixed very soon. The next would be to be aware of the flipped kernel address map after the kernel version 5.4. And it might be that you might see, if you are running a readelf, for example, readelf command, and you are looking at the output of that, you might see different addresses for the pt note or the pt load segments. So don't be surprised. It's basically because we have flipped the kernel memory map starting from kernel version 5.4 for ARM64. Also, newer or willing application owners can give the 52-bit addressing a try. So for example, for that they need to invoke the mmap call with a specific hint to make the kernel return them an address that is in the 52-bit range. And the next is expect more kernel changes around this feature in the near future. So while I'm recording this talk, I already see that ERD has merged a patch set that extends the direct linear map range for the 52-bit configurations. So do expect that there will be more and more kernel changes in the near future around this feature till we actually have it working on a large number of configurations. Also, towards the end, I would say just test the upstream kernel if possible on both the new ARM64 CPUs as well as the old ones. So basically to check the newish 52-bit support in the kernel. Also, if you don't have 52-bit hardware, physical 52-bit hardware, ARM64 hardware, you can always use the free ARMv8 simulator model that is provided by ARM, and which can run Linux and BusyBox pretty well. So you can use that as a experimental vehicle. And at the very last, I just expect to see more and more ARM64 products in the market with the larger physical memories connected to them. So with these 52-bit extensions, it's possible for having very high-end server products based on ARM64 cores, because they can support all the way up to 4 petabyte of virtual and physical addressing ranges. Right. So you can find this slide deck on my GitHub page, and also drop me a message on my email for any further discussions, any further thoughts or suggestions from your side. So I'll be more than happy to start a discussion with you on the same. Right. So with that, we come to the end of this talk. Thanks a lot for your time, and I'm open to take any questions that you might have on this. Please feel free to share the same. Thank you.
So much. That was a really great pre-recorded talk, and definitely shared a lot of context and history as to where that has got to by today. So thank you. We've got a few questions from the crowd. I did want to just take a moment, though, to give you, if you wanted to, just a few minutes, if you wanted to add anything on the back of your pre-recorded talk.
Yeah, sure. Thanks, Pia. So, thanks a lot, everyone, for coming to the session today. I know it's a bit, awkward because of time zone differences and wherever you are in the world. So you can find first and foremost slides on my GitHub account. So just feel free to download them. It's a PDF. And apologies, for some part of the video, the slides kind of, intermingled with the embedded webcam. So you can have a look at the slides separately just to, make more sense of it. But this is a completely new feature, the 52-bit support. It's not, especially on ARM64 architecture, is quite a new feature, and distributions or support is still coming along for it. So you'll be seeing more work, more effort, trying to stabilize it, trying to use it. But definitely, it's a add-on feature for the server market, because it enables you to address ranges quite high up in the physical RAM range. So it's pretty much kind of a catch up that ARM played with x86, because after x86 introduced the file level page tables, so it's kind of ARM kind of did a catch up with that. And so you can see more and more ARM cores coming up with these features. Just try to play with them, and at the same time, whenever you make a change, just keep in your mind that the same software should work ideally on the legacy cores, which don't support these extensions, the hardware extensions.
Yeah. Wonderful. Thank you. Our first question from the participants is, and you've touched on it slightly here, but have the hardware debugger vendors, for example, JTAG ICD, caught up with the memory layout changes?
Right. It's a good question, actually. And in fact, a couple of them I know, the ARM DS5D3 that's coming from ARM itself, as well as the Lottapack. The Lottapack, it's very well used debugger ICD. So it's both of them they are aware of all these changes, the hardware support, as well as what happens to the software map. So I know of these two. I'm sure others, other vendors might be following up, but at least these two I know that they already have support, and they already, you can debug using these debuggers on these new hardware machines, which support all the way up to 52-bit virtualization.
Wonderful. I guess I have a question, just while we're waiting for a couple more to be racked up. And it's a bit of a newbie question, my apologies, but what are the use cases for the large address allocation? What are some examples where it gives you a benefit, and where do you see that going?
So basically, the primary use cases are mainly on the server side. So basically, you can have your 64-bit ARM servers, and we had a few use cases on the supercomputing side as well. For example, Fujitsu recently designed a 64-bit ARM-based supercomputer, which was very, very it was among the in the ratings, in the performance ratings recently. So it also uses this ARM v8.2 hardware, which is capable of supporting 52-bit extensions. So the use cases are mainly stacked on the range where you would require higher memory capacity, like servers or supercomputers. But you never know, actually. With x86, we are also seeing that the file level page table support use cases are now trickling down to medium level use cases like the edge routers, or simply just the routers. So I think that in coming future, other than servers and supercomputing applications, edge routers and normal routers, they'll probably also kind of will like to support this feature.
Okay, so we're sort of seeing this weird divergence where we're getting really big things get much bigger and really small things get much smaller. Do you see that in terms of how we deal with memory addressing? Do you see that converging at any point, or do you think it's just a totally different use case with different needs?
Right. Yeah, it's a good question. Actually, you're right. Actually, because of the different use cases, kind of diverging at the moment a lot, and especially for the server. And I think if you compare the ARM embedded use cases, for example, in your mobile or any handheld device, it's quite different. As the kind of design methodology or kind of use case is quite different as compared to what you would expect from a server or from a supercomputing application. So from on the mobile side, you want your space to be less, power consumption to be smaller, plus you want a compute power which is sufficient for your device, maybe not on the very high side. So probably on these kind of use cases, the embedded use cases, the it wouldn't be much it wouldn't make much sense to have these large virtual addressing support extensions. But especially on the when you move up the scale, maybe in the medium range or on the higher range, all the way up to supercomputers, you will see more and more requirements for these higher addressing range, because we already have seen a server which had 64 terabytes of memory connected to it. So it's quite huge actually, as compared to what we were seeing earlier. So it was an x86 machine, by the way, but still, the same can be true for ARM in the coming days also.
Okay, I'm going to ask a slightly strange one. As we're seeing the containerization of applications, we had containerization of operating systems, and we've had containerization of applications, and this is almost like containerization of memory. How do you see us being able to have auto scaling right down to the hardware requirements evolving over the coming years, and this sort of shift to auto scaling at every layer of the stack?
Yeah.
Does it make
So
sense?
yeah, I think for this particular topic, it probably containerization wouldn't probably be the right paradigm to look at it from, because we are looking at the physical RAM that's connected to the machine. But yeah, I understand your point. We are eventually looking at putting everything into a container, kind of running. So, and container is eventually Linux. Anyway, so when you are kind of bundling it together, so it's easier to share it, or maybe to productize it, put it in the market when you have it in the shape of a container. Plus, you can run it with several other applications running on the stack, so it's quite easy to fit in the container in that particular paradigm. But I get your point. Yeah, but we kind of are living in an interesting world. So for example, we see a very layered approach, even if we talk about some distributions like Canonical or Red Hat. It's quite containers are a very important foundation stone for that. And plus, there are several layers that kind of talk to the containerized Linux, and you get a lot of applications fixed through that. So yeah, I think going forward, it's going to be one of the USBs, that you can containerize something, and you can plug and play with it in the overall stack that you have, or maybe the overall application scenario that you have.
Yeah, particularly when you can start clustering your hardware stack and then just being able to call from it in an effective way.
Right.
Wonderful. Well, we've got still a few minutes to go. We have had some good response from people, and they're very keen to learn about the extensions, and a lot of thanks and applause there. We will, but we are running just a little bit early, so I don't suppose you can help this audience understand how can they get involved, how can they contribute, and
Sure.
and what.
Yeah, that's a good question. Actually, I kind of tried to talk about that in the last few slides I had, maybe the last couple of slides. So basically, the important point is that even if you don't have a hardware, so because the ARM 52-bit hardware is just coming up, even if you don't have the actual hardware, try to play with the newer software, for example, Linux kernel, or maybe the user space applications on your older hardware. So which is supporting, let's say, up to a maximum of 48-bit virtual addressing. Try to play with that, because the software has been kind of changed to work well with both the hardwares, the 52-bit one as well as the older one, which supports all the way up to 48-bit. So just try to make sure that nothing is broken at your end. If everything, if anything is broken or you find issues with it, just try to report it to upstream communities, and people will try to help you with that. Also, one interesting point is that ARM provides a fast simulator model. So I have some interest in simulator emulators, and I can tell you that the ARM fast model, it's called the ARM V8 fast model, and you can download it freely from the ARM website, and you can just plug and play with it. So it runs Linux, it runs your BusyBox init ramfs, so you can basically boot upstream kernel on it, as well as run your basic applications on it. And you can kind of step up the initiative. You can try to compile more applications into BusyBox and then experiment with that on the simulator. Of course, the simulator would be slower as compared to the real hardware, but you'll get a feel of how to use it and what the kernel does when it encounters the 52-bit hardware. Even though the hardware in this case would be a simulator or simulating model, but still you'll get all the way up to Linux prompt, and then you can run your user space applications and you can play with that. So these are two couple of important points. And the third one is, like I said, expect new developments in this area. The memory map for Linux for ARM64 is evolving. We've already flipped it in the sense that what it was earlier as before version 5.4, we have completely flipped it since 5.4, and there are more changes coming up just to accommodate this 52-bit hardware, how to address the 52-bit range using pretty similar model as we had for 48-bit. So we are managing with flipping the kernel map, or trying to fix things in the kernel map. So just keep a lookout for that. And the fourth important point is, what happens to your user space application? So, for example, if you want your user space application, you don't want to modify it. What happens if you run it on a 52-bit hardware or a kernel that returns you pointers from the 52-bit, address range? So first and foremost, the kernel is designed right now by default to return your address in 48-bit range, so that your existing applications work, they don't break apart. But if you want to play with the 52-bit support, and you want your kernel to return to you a 52-bit pointer in that particular range, just make sure that you call the mmap with the right hint. So I have given the links for that in my slide, just how to specify a hint in the mmap call, and the kernel will automatically, if it supports new extensions, it will return you a pointer in the 52-bit range. So you can modify your applications, like your JIT applications or your kernel debugging applications, just to make sure that they keep working with if the kernel returns a 52-bit address as well. So these are the 4 points I think that people can look out for. They can contribute. If anything is broken apart, they can report that to the upstream community and help. Definitely, all the logs, all the we can test only few user space applications, a few scenarios. So if people report issues or they have some ideas about it, it will really help.
Wonderful. You said to keep an eye out for announcements and what's coming next. Where can people keep an eye out? Like where should they keep? Is there something they should?
It's the mailing list for ARM, or the Linux mailing list. Maybe I can just add a link for that in the post chat window. And so basically you will see and the kernel documentation. So inside the kernel documentation, if you look at the documentation directory, there is a placeholder for the ARM64. So just go into documentation/ARM64 and look at memory.txt. So it's like describing the memory layout that we currently have in the kernel for ARM64. So just keep looking for any changes to that, and especially since 5.4, it's been quite updated actually. And it's in the process of being updated just to accommodate all these 52-bit related changes. So just keep an eye for any changes in the git log on that particular kernel documentation file.
All right, just a final question, and it's a little bit more speculative, so bear with me. But you've got an audience here that's clearly interested in ARM64 CPUs and support around that. Given you work so deeply in the space, are there any other, I guess, major changes or competitors or shifts in the architecture and options for people in this space that might be worth them having a think about or keeping an eye out for?
Yeah, just to give a brief background about that, there are a lot of different cores coming around from ARM, so they are kind of suited for different environments. So, for example, for the Amazon instances, the EC2 instances that we have for the cloud-based requirements, they are based on the Graviton CPU or the Neoverse CPU, and there are different application profiles. The cores are for different application profiles. So, for example, usually ARM has three type of core families: the A family, R family, and the M family. So A is for mainly for the application use cases like servers or routers, whereas R is for real time. So it's mainly for real time applications like maybe some your which require you to run a RTOS, for example, and in series, which is mainly for MCU. So it's kind of smaller, maybe very little MMU support, or sometimes even no MMU support. So just keep in mind that whenever you are looking at the ARM core, which kind of use case it kind of targets. So the A core is kind of the more powerful one, mainly for the higher end applications. The R1 is mainly for the real time, and similarly the M1 is for the microcontroller one. So just keep an eye for these three different categories, and just look at the evolvement of the overall architecture. So ARM has kind of released its architecture in several different versions. So it's like ARMv 8.1, 8.2, 8.3. So with every minor version, new features are being added on. So just keep a eye on that. You can look at the info center. So I provided a link for the info center, or the ARM info center, in my chat window in the Blimmings Lab. So I'll just post it on the post session chat channel also. So just have a look at that. You can download a ton of documents there freely, and just have a look at them, and they'll basically kind of get you started. What kind of JTAG debuggers are there which support which kind of core, is suitable for your use case, what's the support available for that. So it's they have even a software programming guide for your processor. So just have a look at that if you want to port Linux onto it. So there are several interesting useful links available there.
Wonderful. Look, I think we might wrap it up there. We're almost at time. So thank you so much for the talk and for the Q&A chat afterwards. Really appreciate it. If anyone has a last question, this is your final chance to ask it here. Otherwise, Bhupesh will be able to join folk in the Blimmings Labs post-talk Q&A channel on the Venulus. And it's also probably worth the folk here who weren't in the earlier presentation by Peter Chubb might also find that one interesting as well, about applying statistical methods to performance measurement for kernels, so for kernel performance. So that might also be an interesting one for the same audience. So thank you again so much for the presentation. What's coming up next is there's a 10-minute changeover, and then we'll have Neil McGovern on Patently Obvious, the year that lawyers came from foss, talking to us back here in Blimmings Labs starting at 4:40 AEST. Thank you all so much, and thank you again so much, Bhupesh. It was a really great presentation.
Yeah, thank you.